Okay, I think we'll get started. So today we're going to talk about solvation of ions into solution. And we're going to talk specifically about an important model called the Born model. And this is one of the most common, what are so-called continuum models for a solvent. It's handy in getting rough estimates of how ions will solvate into solutions and between phases of solutions. So we're going to look at some of the details here, and then we're going to do a bit of an application to pharmaceuticals. All right, so in a real system, we've got some kind of ion. If it's an atomic ion, such as sodium, then it really will be quite spherical in shape, but it could be a polyatomic ion, not quite spherical. So this could have some kind of shape, certainly has some kind of electronic distribution about it. And this will be then placed from the vacuum into some solvent. And the solvent itself might actually even be bigger as individual molecules than the ion. And certainly it is very, on the scale of the ion, it's very heterogeneous as to where other solvent molecules are. So this is a really quite complicated problem to solvate this ion into a real solvent. So what we do with the Born model is make some simplifying approximations. And the first of these is to move to what are called continuum models of solvation, where we treat the solvent simply as a continuum, as if there's no such thing as atoms and molecules. So you could think of it as just a constant bath of some kind of generic solvent. In the Born model, the only parameter that matters in the solvent is its dielectric constant. So this is a measurable thing. We can easily get the dielectric constant for most solvents, and we just look up the dielectric constant for most known solvents. What the dielectric constant is it captures in one number the ability of the solvent to respond to the charge of an ion. So when an ion goes in, the molecules in the real system, the molecules around it, will align and readjust in order to minimize the effect of that charge. So nature does not like bare charges. We put the charge into solution. The solution will adjust to sort of mediate that charge. And so what that means is if we've got an ion here, we put a test charge over here, compared to a vacuum where we feel the full Coulomb force, we feel some fraction of the Coulomb force. And that fraction of the Coulomb force is the dielectric constant. So if we feel half the Coulomb force, then the dielectric constant is 2. If we feel 1/10 of the Coulomb force, then the dielectric constant is 10. So it's what you divide the Coulomb force by based on the fact that this ion is in solution, and that solution has adjusted to help mediate that charge. So we treat the molecule, or we treat the solvent as simply one number, the dielectric constant. Then we give two numbers to the ion, a radius of the sphere, so we treat it as a sphere of a given radius, and then we put a surface charge, just a charge only on the surface of that sphere, of the oxidation number Z times the fundamental charge of an electron. So if it's sodium, then this will be, sigma will just be one fundamental charge, and so on. Okay, so now what has to happen is we have to get that ion from the vacuum into solution. And in a regular solvation, that would just go in. That's the path Mother Nature would take. But we're going to treat this as a we're going to take a reversible path from here to here. And we've learned now that if we can calculate the work which is not a state function, but if we can calculate the work on a reversible path, then that is equal to the Gibbs free energy. So what we're going to do here is get the Gibbs free energy for the solvation of this into the solution. But we're going to take a different path than what Mother Nature does. But as long as we're reversible, each step along that path will be equal to delta G, which is a state function. And so we're going to get a delta G here versus here, or a delta G vacuum to solvent. Now, how do we do it? Well, we are going to actually discharge the sphere in the vacuum. So we're going to take an infinitesimal bit of charge, d sigma, off to infinity. So an infinitesimal amount of charge, d sigma, will be directed out to infinity. And then a little more, and then a little more, then a little more. So we're going to discharge that sphere. And we're going to calculate the work in doing that discharge. So over the course, our charge is going down, and we're pulling that from R to infinity. So we're going to discharge. So we're going to integrate, little calculus here. We're not going to do the integral, we'll just jump to the other side, but we'll just show you this for those of you who've had some calculus. And if you have had some calculus, you can try to get the result over here. So we're going to drain the charge from ZE down to 0, and we're pulling it from the radius of the sphere out to infinity. And this is just Coulomb's law. So right here is just Coulomb's law. When we calculate this work, we get this answer. Okay, so we won't do the calculus, but the charge will end up being squared, and the radius will go from it'll be 1 over the radius. And so we see here we've got just this this formula. Now, we're going to transfer this neutral charge across from the vacuum into the solvent, and so we're going to do some work for transferring. So what is that work? That work would be ripping open the surface. There'd be some surface tension work, right? And then there'd be evacuating some kind of cavity to put the solvent, to put the ion in. Then there would be closing that up, so that would be surface tension work. Well, let's think about the surface tension work first. So that'll open and close. If we do that reversibly, right, that should cancel. The amount of work to open will be equal but opposite the amount of work to close. And then what we do is we take as an approximation the work to make room for the ion to be 0. So that's an approximation of the Born model. And so ultimately, we take the work in transferring the charge as 0. Now we are in the solvent, and we're going to bring the charge back from infinity, so we're going to recharge the sphere. And as we're bringing the charge back, if there's charge on the surface, they're going to feel each other with a Coulomb potential. And so as we bring this charge in, if there's solvent there, that'll mediate that Coulomb force. And so it won't feel as much. And so it won't feel as much by a factor of the dielectric constant. So we divide by the dielectric constant in the integrand of this integral. And so everything is exactly the same, except in this integral, these will be flipped, and there'll be a dielectric constant in the denominator. So equal but opposite, so plus, everything's the same, and then we have this factor of the dielectric constant. So that's the only difference. So then we can add these all together, and we get the delta G from vacuum to solution. And this is called the Born model of solvation. So we're charge squared, and we're 1 over the radius. and then the dielectric constant. So the parameter of the solvent, the radius of the ion, and the charge of the ion, the oxidation state of the ion, or the charge, are the parameters in the model, the only parameters in the model. So let's look at this. So dielectric constant is always going to be greater than 1 because the vacuum is where you're going to feel the most. Any solvent will be will reduce compared to the vacuum. Now if it's air, air is almost like the vacuum. I think the dielectric constant is something like several zeros here, maybe 3, 4 zeros, and then some numbers here. So the dielectric constant of air is essentially 1. But the dielectric constant of water, for example, is 78. The dielectric constant of octanol is 10. Dielectric constant of oil is about 2 or 3. So these are all numbers greater than 1. So if we look at our formula, we've got 1 over a number greater than 1 minus 1. So this thing in parentheses will always be negative. And then what do we got here? We've got charge squared. So whether it's chloride, negative ion, sodium, positive ion, it'll be getting squared. And then everything else down here is positive. So this whole term is positive. This term is always negative. So this fact implies that delta G vacuum to solvent is always less than 0. And that says it's always favorable to solvate an ion into solution compared to the vacuum. And nature does not like a charge in a vacuum, and definitely favorable to put the ion into solution. So whenever delta G is negative, that means the process will thermodynamically want to go or spontaneously want to go forward. So solvation is favorable. Let's look at the effects of the parameters. Increasing so as the dielectric constant goes up, the magnitude, let's go with this. Right? So the size, it's always negative delta G, it's going to get bigger, right? So the absolute value of delta G goes up because we're taking, this is a difference, and if this goes up, let's take it to infinity, then that would be 0. Anything less than infinity, that would be 0, this would be minus 1. Let's take this to be 1, that would be 0. Those are the two extremes. So anything else is going to be somewhere between 0 and minus 1. And as this gets bigger and bigger and bigger, this term becomes less important, and we get closer to minus 1 in this parentheses. Thus, this goes up. Let's look at the oxidation state, Z. So as Z goes up, the absolute value of this goes up. Okay. And finally, let's look at R. R is in the denominator here. So as R goes up, the absolute value I shouldn't do this. That's always true, but it goes up, sorry about that, up, and then this goes down. So let's say we go from sodium to potassium, then it's easier to solvate, it's more favorable to solvate sodium than it is potassium. Likewise, if we go from, say, let's see, maybe calcium and sodium. I'm not sure, we'd have to look that up, but I think the radii are pretty close. So they differ by a +1 charge and a +2 charge. It will be more favorable to solvate the 2+ charge calcium than the 1+ charge sodium. Okay. All right. Well, that's interesting in and of itself, but a more practical use of this is when we're actually going between phases, alpha and beta. So let's say we have two liquids that don't mix, and we want to say what's our delta G for an ion to go from phase alpha to phase beta? So alpha to beta here. Well, just like before, we're going to discharge and charge. We're going to call the work transfer equal to 0. Again. And what's going to happen? Well, we discharge with dielectric constant for alpha, and we charge dielectric constant for beta. And so when all is said and done, we get this stuff out in front, just like we had before. But now in place of the 1, we've got the 1 in the solvent, we've got the 2 different solvents here. So let's check this out. Let's take oil. Let's let alpha equal water. And actually, just to set something up here, let's let beta equal octanol. So water has a dielectric constant of 78. Octanol has 10. So let's look at this parentheses here. 1 over 10 minus 1 over 78. Okay. Well, this is going to be a positive number, right? It's going to be a positive number. And that says that this whole thing would be positive. And so it would be unfavorable for an ion, always unfavorable for an ion to go from water to, because water is alpha, water to oil, okay? Or octanol. Unfavorable. And in fact, let's generalize this. It's always more favorable to go from a lower dielectric constant to a higher dielectric constant. And if we take ourselves back to what the dielectric constant means, dielectric constant is how the solvent can accommodate or mediate that charge. And so certainly the more it can, the better it's able to solvate. And so we see that playing out in the Born model. Now again, this is a continuum model. This is ignoring any kind of interaction between the solute and the solvent, which can radically change things. For example, hydrogen bonding or something like that. But this is just an approximation model for this type of thermodynamic phenomena. All right, let's look at an application of this. So this is true always. So it's certainly going to be true under standard conditions, which we'll indicate here with the circle, the superscript circle. So standard ambient temperature and pressure. So 1 atmosphere pressure, 298 Kelvin, and 1 molar of everything. Well, we have seen now that we have this important thermodynamic relationship for delta G is minus RT ln K. Well, now we need to interpret the K. The K is something we call the partition coefficient for partitioning from alpha to beta. And we write it like this: P beta over alpha, beta being where we're going, alpha where we came from. P beta alpha, if we solve, let's solve for that. So we have delta G alpha beta equals minus RT ln P beta over alpha. So let's solve for this. And get this. All right. Well, how are we going to imply the Born model? We have to make one careful change here. This is talking about one ion. So if we're talking about a single ion, I'm going to just tell you this for now. We replace R with Boltzmann's constant, Kb. So I should make this a Kb here. And you could try for yourself. If you multiply Boltzmann constant by Avogadro's number, so we have 1 mole of something, we get R. So if you're talking per molar, then you use RT. If you're talking per molecule, you use KT. So I'm going to have a little change up here. We're going to have a KT up here. So here's our KT. That's coming from this RT. Then everything else is coming from the delta G expression for the Born model. And so this would be a way to estimate the concentration of the ion in beta versus the concentration of the ion in alpha. Now, this plays a very important role in pharmaceuticals. So anytime there's a drug, there has to be data associated with that drug, and one piece of data is the partition coefficient. And the industry standard is to use water and octanol. Octanol does go in very slightly into water, not perfectly immiscible as they're called. About half a gram will go into 1 kilogram of water, so quite immiscible. So we get 2 phases, octanol sitting on top of the water, because octanol is less dense. And you put this drug into the water-octanol mixture, and you see how that partitions. Now, oftentimes this goes beyond ions, although certainly some drugs are ionic in form. So here we're talking just about ions. But if we extend a little bit to this idea of the partition coefficient, then in general, we're looking at how much of our drug is in the octanol or oil phase and how much is in the water phase. And based on that, that can be one factor in deciding how to administer that drug. So if we go water to octanol, if we write our expression that way, then PO for octanol over water, W for water. If it's low, that means that the drug favors water. It's hydrophilic, favors water. If it's high, then it favors oil. And if the drug is high, a skin patch may be used to administer the oil, or administer the drug. If it's low, we may have to use injection. And if it's somewhere in the middle, it might be administered orally. Now this is just one factor. For example, if you administer the drug orally, will it hold up under the conditions of the stomach, the acidic conditions of the stomach, or the basic conditions of the duodenum and rest of the small intestine? Those are other questions associated with the drug. But this is one indication. So let's try to understand that a little bit. If it's low, the drug is not going to want to go into oil. So our skin is quite impermeable to water. So if we put a skin patch on, the drug's going to want to stay in water, not really want to go into oil. So it would not be very effective. But if the drug tends to want to go into oil, then a skin patch could be very effective. One example that you might be familiar with are the nicotine patches. So nicotine can pass through the skin that way. Otherwise, we may need to inject the drug if it doesn't go into the oil phase very well. All right, so this is the Born model of solvation. It's one of these continuum models, as they're called. We have just 3 parameters: the charge, the radius of the ion, the charge of the ion, the radius of the ion, and the dielectric constant of the solvent. We can use 2 solvents, 2 miscible solvents, and get a partition coefficient from one solvent to another. And this is used in many places, but one place in particular in pharmaceutical industry.